3-foot wall with a green system.
Okay, I can let's look the color form equations. Well, it's okay. Easy.
Let's go ahead and get started. We are very happy to have Arkady Vainshtein visiting us today. Tell us about supersymmetric 0,2 sigma models in 2 dimensions.
Okay, I certainly appreciate the invitation to this around place. I mean, impressive building. Last time I was here, it was, I believe, 2006. My impression, I understand that the building was not around. Yeah, so it's, I mean, okay, I mentioned to Ben that maybe you need some kind of object of arts to put around, because it reminds me of Guggenheim. Yeah, but the subject I'm talking here was chosen, I don't know, who was by the group here, and I'm trying to together with my thanks to say that to apologize that what I'm talking about is not that fresh. It's 2014 actually, and we work on this together with Misha Schiffman, and okay, Xiaoyi, she used to be his student from China, I mean originally from China, and Jin used to be my student at that time. So we spent some efforts to follow this up. Okay, and I'm not sure how much I will spend time on the explanation, but it is another subject partly related, also about heterotic two-dimensional models. It means that there's this kind of asymmetry between right-handed and left-handed. And it was paper study we did with Schiffman and Alexei, Mikhail Schiffman and Alexei Jung, and it's kind of QL-like CPN model. So when you have connected models, the reason we went there was that with this heterotic model, you have spontaneous breaking of supersymmetry, and these connected models, which is not exactly QL, but I would say QL-like, we found possibilities that supersymmetry could be preserved. Okay, now here is this outline of the talk. So these 2 parts, one is about this heterotic models, and another, I mean, a continuation of this connected sigma models. Okay, and the subject which okay, the first characterization of the model. For us, we spent some time with this perturbative analysis of this model. So we did calculation up to this 3rd loop for coupling in this model, but then we spent in detail trying to find this kind of exact relation, analog of four-dimensional exact beta function, and we found this one. So I mean, explicit calculation, you can verify that they did match this. And there were some tricks, so it was not full analog of NSVC beta function in 4 dimension in terms of derivation. It was some specific of 2 dimension. Okay, now, okay. Now I'm trying to remind a little bit of history that, say, sigma model, okay, here it is a reference to such Polyakov paper of 1975, okay, and this what I call heterotically uniform and equals 0,2 CPM It is kind of well shaped for non-abelian strings, and n equal 1 in wheels in 40. It is a stuff where this work studied by Arkady and Tong, as well as Schiffman and Jung. The idea is that you have kind of solitonic object, stringy object, and then you would ask yourself what is world volume theory, what is the theory of this thing, and then it will be two-dimensional theory there. And in this way you are arriving to this kind of heterotic models where you have this not n to 2 where you have equal number of right-handed and left-handed, but 0, 2 where it's not the same. Okay. One of the interesting features of this two-dimensional model is, of course, parallel with four-dimensional, and as you know, there are certain stuff. Some evidence like asymptotic symmetry, different phrases. There is n equal 1 solution. There is also, in terms of say supersymmetry, there is this certain cases where this four-dimensional Zabig-Witten stuff is matches one-to-one to two-dimensional, and it's for special points, but there is this one as well. So I will try to discuss this geometry of the target space in this case, and particularly in this class it's related to beta function, it's holomorphy, and how it's preserved and not preserved in this two-dimensional model. Okay, so I already mentioned that for isotone is important as well. Okay, stuff I'm not sure how much time I will have to discuss, but still it appears to be very much related to supermultiplet of anomalies. And you can, we actually did trace a relation between kind of anomalies and this beta function which appears there. Okay, at least explicitly up to the second loop, we check that the relation is fulfilled. Okay, so in this way, again, kind of not full analog of 4D, but similar to 4D in this respect. Something.
It's not very fun.
It went from. Okay, here I put a lot of this equation here. You shouldn't feel yourself obliged to follow it, but still maybe to show that I use this equation. How to say, when we did it, we spent the efforts to do this superspace analysis and all this stuff, and maybe we put to many equations, but still, and I didn't put here on slides all of them, but still some number. So here, to start with, it is this parallel supermultiplet. So you see lowest component is scalar field, heat is left-handed here, and left and right x, okay, it's the usual t plus minus x. Okay. Another one is called Fermi multiplet, starts with psi. So it has psi and auxiliary field F. So essentially, in terms of physical field, you have phi. Scalar, left mover psi and right mover psi. Okay, it is an kinematics of two-dimensional. Now we can compare this superspace in 2,2 case. Here it is superfield, which is of 2,2, and here you have in this way you have there are two tethers, left and right. Okay, and what's going on when you are going from 2,2 to 0? Then we are calling up one of those theta, so theta r is there, but and I call it theta, but I mean it is what used to be theta r in 2 by 2, 2,2. Okay. Now here in case of CPN, okay, what are this A and B? Something is missing here. Not missing. No, here it is. So we have n minus 1 field. So this starting from this. So you have in this way, of course, equal number of left-handed left mover and right mover in 2 by 2. But then we are changing it, and this kind of modification corresponds that we are adding up one fermionic field, which is called here B, calligraphic B. No, essentially you are adding up one light move. Okay. And then let's look at the Lagrangian for this one. K here it is Carry potential, I mean derivatives of Carry potential. And the additional term, you can see it is associated with this kappa, which contains this B field. Okay, and here it is like kinetic term for those B field, but this additional light mover, it is the one which induces heterotic structure, and and also brings in new coupling kappa here. Okay. So, as you know, Carry potential is not uniquely defined because you can change it, and in even first derivatives are not uniquely defined, but metric, which is second derivative of Carry potential, which is the one which is good object, good tensor. The reason I'm discussing which tensor is good and which is not, it's related to the holomorphicity, because we are looking for analog of, kind of gauge coupling, right? Which one would be gauge coupling is coefficient for F term, and it is what we are looking here. So Lagrangian could be written in this form: integral over 1 theta, not of F, and F is written here. However, then we need to find out which term. So essentially would be one term only would be F term, would be another T term, and it is written the same in this form. You see that this term would be F term, it contains this normal tensor. This term would be D term. I mean, this D, it is like second integration over second theta, right? So this one, it's a kind of analog of superpotential, if you like.
Okay. The curly B, if I turn that off, this just becomes a standard 2, 2.
Yeah, right. Yeah. So if you take this, you see that this B, if you take this off here, this is normal kinetic term for both. But in normal kinetic term for B, it's in the 2, this kinetic term will be related to another kinetic term, but when I broke to 2,2 to 0, then generically it stopped to be related, right? So you see, it's kind of D becomes F term accounting for 2,2. Then it's okay. So
what is Z in the calligraphic Z?
It's a different, it's a wave function normalization, and it is, you see, different tone. Here it is the original B, and here it is the one which I added up.
No, but are these constants, or are these like?
It's just constant, yeah. So you see, but we are discussing movement of this, yeah. So I mean, in this way, when you are going for correction, you will, compare with normal gauge theory, you have gauge coupling tone, but you for the matter you have Z, right? For the matter tone, you have Z there. Then you can discuss whether it's quantum physics or not, but Z will be there as well. Okay, so no, and as important for group consideration further, and here it is in the same expression, but how it looks in complement. I mean, okay, so you can see that this part without kappa, I mean, you can check that it is the same as it was in 2, and there are additional terms which are related to kappa, which contains this zeta r. This zeta r is the one which I added up. I mean, okay. This term, it's kind of induced term, right? You see, it doesn't contain zeta r itself, but it is there. So, metric example for in particular coordinate. This round coordinate, this example of how this metric looks like in CPN model, where chi it is the sum of all this field here. Okay. Okay. So now, okay, here it is. Discussion of the spaces we are talking about. So it's homogeneous spaces which contain this group G divided by stabilizer, whatever H. And for CPN, G is SUN, H is kind of product of UN minus 1 U1, and okay, and in this particular case of Grassmannian, where this H is this group. Okay, and in homogeneous spaces, they are also what's called Vainshtein spaces because curvature is proportional to metric. Okay, and coefficient here B it is okay. Do say the number, or I don't know. We used to call it Dynkin index, which all essentially up to coefficient is the same. Yeah, but and for SUN it's just N. Okay. So beta function in loop 2 it is one loop. Okay, and it is the answer for a loop, and beta function is given by this Tg. Okay. Now we are trying to discuss what happened with geometry when we introduce this heterotic modification. So in this heterotic modification, okay. You see, I'm trying to so what is a manifold? It is manifold of CPN, which I did try to discover. But what we add in up, it is C. Okay. If it would be bosonic stuff, which itself. Remember, you can talk about whole volume theory on the stream. Okay. You imagine you have seen, then you can have something associated with transversal coordinate. Which are not entered in the same description. If it will be bosonic, it will be this coordinate, but then you will say, aha, this extra coordinate corresponds to free field. Okay, so you forget about this free field. Okay, what happened here? Then now you say, aha, this bosonic direction which involves only free bosonic field, but let's introduce this tangent bundle associated with this extra coordinate and introduce fermions there. So this tangent bundle, it is tangent bundle of stuff contained in this. Now, while it was free field for bosonic part, it's not free field for fermions, for tangent bundle of fermions. Okay, it is an interpretation of this. So in this way, you can say that your manifold is this one. However, bosonic part of C is irrelevant, does not enter, but fermionic part does enter. Okay, so here it is effort to explain. So let's say that our extra fermion B, it is we had n-1 fermion, we added 1. So let's call this added 1, let's call it Bn. I mean, n-1 was already in n equal to. So then I can write it in this form. Lagrangian, and here it is metric, and now metric includes this additional field. Okay, and So that's why I allow this. You see that this effector enters, one effector enters in this component, and another effector enters component which are n and bar component. Okay, so you can view it as this expanded expansion of the metric. Okay, and this then the T here is also has component here. Okay, it's shifted. So there is component, mixed component, the one which is associated with kappa, and there is a K component which is which we are normal one. Okay, I'm sorry that here I did try to correct it, but something happened. This potential K not uniquely defined, but what is defined is the derivative of this potential. Corresponding curvature is called H here. Okay, so you have H. I mean, in n equal 2, I mean, it would be this the same. H would be when it ij and n, then H would be just metric, like up to coefficient. Okay, but the other terms would be, I mean, the I mean, no, I mean, it is normal part and it is additional part, which are associated with the fact that you send. Okay, so now we have this Lagrangian in such a form. It only part associated with B fields. There are of course A field as well, but here it is B field, and you see that this non-trivial interaction involves this derivative here. Okay, this heterotic interaction, and it enters through this curvature. Okay, so why it's important that, because remember I'm trying to follow holomorphy, right? So this would be a good term. I mean, in terms of describing that it is like a superpotential. It means that, for example, it would be having no Renorm-Gilles correction, so it would be no heterotic correction. So okay, here it is the main action. Yeah, I did try to get consultation of mathematician, particularly Alexander Voronov, who is in this algebraic geometry. His advisor was Yuri Manin, actually in Moscow. Okay, and so for him it is to call action of C star one-dimensional group on odd vector bundle. I mean, no, the construction which I try to describe. Okay, but my mathematical ignorance did not advance much. Okay, now after this discussion, we can discuss this holomorphy and where it's preserved and how it's not, when it's not preserved. So in terms of homomorphy, we have, okay, in terms of parameters, you see we have 1 over G square coefficient, which was original metric there. Then we have this K in units of G square. No, it doesn't matter, but okay, convenient. And we have two wave function renormalization for B field and B calligraphic field, Z and Z star. Okay. What I did like to demonstrate before corresponds that 1 over G square and K over G square both are holomorphic algebra. In particular, 1 over G square is standard that imaginary part of 1 over G square is what's called theta over pi. Okay, so you can view this coefficient 1 over G square as a complex one in the equation before. And it means that, in particular, that, for example, this is like superpotential. It means that K over G square doesn't depend on a renormalization point. We are using UV cutoff as a normalization point, as our normalization point, so it's written in the form. So you can say that all this quantity here depends on MUV. Okay, and then we discuss how they depends on MUV. Okay, it is so this would be there. For 1 over G square, it's a little bit more complicated. You would say, aha, it's holomorphic. coefficient, and no correction. But the same statement that 1 over G square is coefficient for holomorphic quantity, it was true in 4D. So you would say, there is no running of Coupling constant in 4D, which we know not true, right? There is, okay, and 2 case was one loop, but still it was running. So, what was a consequence of this holomorphy was that actually the only one loop collection were for 2 cases. There was no higher loops. But when we are breaking n equal 2 to in say in 4D, but then we know that there are higher loops as well, and these higher loops correspond that holomorphy is not protected. The holomorphy is broken. No, here it mentioned paper by Dixon and Kaplanowski and Lewis, 91, where they constructed the model where it happened at one loop. It was certain masses dependent, but and we did try to follow this with Shipman there. Okay, to discuss how this holomorphic breaking is occurred. Because in some way the idea is that holomorphic breaking actually occurs due to Z factor, due to wave function minimization. Even in a pure gauge case, because you can say, 1 over G square plays a role of Z factor. But in this sense, you can kind of find out that because when you go into second loop, it's indeed you're using 1 over G square as Z factor, and the origin of breaking of holomorphy appears there. But instanton in particular appears to be a very nice object to follow, because then you can find out that while in perturbative sense is broken, you still can find out how to in which quantity is preserved for certain instantonic calculation, and then it gives you this exact beta function. Okay, so here I'm sorry. Here, in our 0, 2, we have this breaking at the first loop. And it is, happens due to this coupling which we introduced. Okay? Here, it is a diagram which one loop shows this. Okay? So, okay. I mean, it's like a normal Fermion, and it is this theta R Fermion here. So we see this polarization operator of which includes you see two propagator, but one is a psi and another propagator is a zeta, which we introduce is the vertex is proportional to kappa, so it's kappa square, and it is the answer for this diagram. Jij is this metric, original metric we started from. So you have this correction to Lagrangian, which is written. No, I mean, and outside it is a bosonic field. So you have this result for correction to due to this fermionic exchange with the sun, and it is explicitly holomorphic breaking top. Okay, this could be written in terms of this curvature. Remember, I mentioned this curvature, so it's the same expression, but kappa is absorbed into this curvature which was introduced. Okay, now we are trying to follow up this breaking of holomorphicity more explicitly, because okay, at one loop it is very simple. Instead of 1 over G square collected by this term H square over pi, where H it was kappa over G square. I don't remember, it was probably written where. no, okay, it would be further. No, H is the same as cup, no, I mean up to G squared. Okay, so you have this stuff, it's interesting enough that you have this explicit diagram which breaks holomorphy here, and it gives you this result. On the other hand, if you do instant calculus, this theoretic interaction does not give you kappa squared term in instant calculus at all. And it means that in difference between relationship, instant action stay holomorphic at least at one loop. So instant action, it is 1 over G squared, but this 1 over G squared should include this, A square correction. So you see that what is written here, right? That instant not sensitive to this. However, G is redefined. Okay, and it is kind of unusual situation here. Okay, so then we return back to instantonic action. So you have instantonic exponent, you have coefficient corresponding to 0 modes here, and you have power regulated corresponding, to this. Okay, I should start with this. So you have for each 0 mode you have M, and you have square root of C. Okay, so here it is the result. And what is important is that this one, this instantonic stuff, is a long loop invariant. So you can verify that there is no, when you go in higher loops for instant on calculus, there will be no higher loop correction. But it contains already, this what I mentioned before. It contains this A square over G square stuff included into definitional version. So there is another one which I mentioned before. Remember this coefficient, which was like superpotential, which has no correction in this case square over G square. So in other units, okay, H square over no, I mean it is K is H over cap definition of H, if you like. So here, which enters there, and it is also a non-loop invariant, okay, in this notation. So we have two non-loop invariants. Now we can differentiate to get expression for beta function, for example, beta function of G squared. So in principle you have two counterpart, but okay, one is fixed by this one. You see essentially, so you have beta G, and when we differentiate, you will get this equation which you can compare with 4-dimension, where you see the analogy. So you have terms which is anomaly dimension here as well, but what is additional one is that you have here also anomaly. Okay, here, I don't know how to say. Okay, remember that the result was fixed by knowledge of anomalous dimension. Here and here is also anomalous dimension, and there are two of them. One is Z and this Z tilde, right? So one related to this heterotic additional fermion, and also another analogy is that it was this geometrical progression in alpha over pi, and here is also the geometrical progression in H square, and it follows just from this invariance of this one.
Can I sort of hear
yeah.
What the effect of the 2,2 breaking field? Can I isolate it in the
In this sense, I would say that the H itself, it is no, because if you put kappa equals 0, there is no, there is no this heterotic structure. Okay, then you should be back to but in this case it's very simple, right? Because you are back to n equal to 2. Right. So here it is beta function for H square. Okay, we have two invariants, so we have two relation. And here it is, okay, it's not independent, it's just instead of h, you can consider this ratio h square over g square. I will explain why I will mention why it's interesting, because you have this beta function for this one, and okay, probably I should mention that there is a fixed point in law. There is a special point in law which is a fixed point. So it's here it is just reminded the definitions. That beta g is defined as a derivative of g squared, beta h is the derivative over logarithm with the valid normalization point, and gamma is this one. And you see this exact relation, the same as in 4D, they do not fix anomalous dimension, so you need to calculate anomalous dimension, one loop, two loop, or whatever, but then beta function for holomorphic quantities like E1 over G square, this beta function is fixed by anomalous dimension there. Okay, so here it is an example in one loop. So in one loop, anomalous dimension, you can find out that it is okay. The two pieces. So there is this gamma for theta field, this one, and not very much visible, but it is sum of this gamma, which is sum of all gamma, which enters into this equation. Okay. Key here in this notation, it is dimension of the manifold. Okay, maybe the word complex dimension is not good, but dimension is measured in counting complex field. In this sense, D equal n minus 1 per CPM. No, it's a kind of standard one. Okay. Okay. Here, I do not need to spend much time on it, but just to mention that we did explicit 2-loop and 3-loop calculation. So in this way we could compare, this instantonic derivation with explicit correlation. No, okay, a little bit more than that, because when you are doing this 2-loop and 3-loop correlation, you are knowing anomalous dimension further. So in this way, this exact formula allows you to go one step more in beta function for G square. Because you know anomalous dimension for 2-loop, you know beta function for G square in 3-loop. I mean, the relation between this function is exact. Okay, so in this way, it's not only to check, but also it gives you, one loop more prediction for beta function. Okay, so you see here it is 2 loops there and 3 loops for beta g. Here it is 2 loop result for beta h and beta rho, and from here you can see this fixed point I mentioned. You see that at rho equals this one, you have 0 for rho. So rho does not run if you choose it this way. Okay, and it's very nice simplification for beta in this form. So beta becomes this simple expression at this fixed point. Okay. Here, I probably will try to save time for the next part, but just to mention that we have this hypercard. Just remind that there is this problem of anomalies and super multiples of currents and anomalies. So in 2.2 we have okay, we call it hypercard because the problem is this. This in superspace, how to call this superspace current, right? Which includes energy momentum tensor and supercurrent for supersymmetry, whatever. So I'm not sure whether it's useful notation, but we call it hypercurrent. Okay. So this hypercurrent has different components. So this one it is energy momentum tensor. This one it is, supersymmetry current, okay, and here it is some kind of vector current. It starts from vector current. Okay, and it is super field notation for this. And in 2.2, we have anomaly. Okay, it's interesting for me that it was the same year I was here, 06, but we considered calculation of this anomaly and together with Roman Zwicky and Mr. Shipman, and HET is expression for, so this could be formulated as anomaly, because if you write it in component, you will see that it contains like TAMU and stuff, and this stuff in the car, and gamma mu multiplied by S mu equal anomaly. Okay, so here is this equation.
Confused by this equation. I mean, is this really a 2,2 here?
No, here is, yeah, 2,2, yeah. It is 2,2, yeah. So not 0, here it is how it changed when we go into 0.
Now, I guess I'm confused by the real equation. It looks like you're breaking the 2,2 supersymmetry.
Where?
In the second block of the equation.
Yeah, okay. In which place?
Well, you're not writing it. I mean, in principle, I should be able to write this in terms of generic alpha and beta.
Yeah, right. We can write it in terms of alpha and beta, right? So it is. No, we just found it's convenient to formulate, because you can check that it is sufficient. What is written here is sufficient. But I mean, we started. You see, we introduced this T alpha beta in the standard way, and then and you can rewrite it in kind of in terms of summation, but it would be equivalent to what is here. No, I mean, it's not breaking over to 2. It's just writing in this for this component. Okay. So what happened in 0, 2 that we have now? I mean, we do not have this. So you see that here it corresponds that we have this SLL stuff, and it is one of currents and another current which called this RR current, and it's it splits these different components which was before into 2 together. It splits into 2 tensor. Okay. Now it was consideration by Dimitriescu with Zyber for considered anomaly, in this two-dimensional theory, and there is formulated in this way. You see that okay, that you have kind of the super potential W and anomaly written in this way, and there is here is in explicit expression for W. Okay, here it's related for arbitrary manifold, not just for a CPN. But the point is that you can discuss anomaly in terms of this object and look for higher order correction and see what we did, and it's what we try to do. So in particular, it is this classical equation, and then here it is an anomaly written here, and then I didn't write all this formula, but we check that this part, which is here, is in one-to-one correspondence with this beta function, which was derived before. I mean, we checked it up to second loop, I believe, normally, but you can see that it's relevant. Okay. Now, in the remaining 15 minutes, I try to discuss the second part about this preserving supersymmetry, because look, in this case, which we discussed, you can view that once we have the 0,2, that generically it is spontaneous breaking of, you can view it as spontaneous breaking of supersymmetry, and Gaussian is explicitly present with this massive fermion, you have explicit presence of Gaussian. And for us it was interesting to find out whether we can preserve kind of supersymmetry without this breaking. And here it is this analog of period, not here it is what is written here is normal period in say the KC, when you have some number of groups and you have quite fundamental fermions which are transformed under closed group. But for CPN or two dimension, we can consider also manifold which is like a product of CPN. Okay. And again, we can. What's the idea is that you have product of CPN. Then no, if they are not interacting, if there is no object fundamental for this group doesn't matter, right? It will be independent CPM. But now we are introducing Fermion similar way as before in a tangent bundle of this product of CPM. So it's similar to what was done before, but now we have Lagrange, which is, you see, the sum over kind of flavors of fermions from 1 to n. Again, and each part it is similar to the part which was before, but now we have, this additional fermion interaction with different fermions there. Okay, and it just gives you a connection between CPM. So very specific form of connection. So okay, here it is the same expression in components, but I mean, again, it's what we discussed before, that it is tangent bundle of the CPM now in power n multiplied by 1c, this additional fermion being introduced. And here it is a formula which, I mean, also was there for CPM. Okay, now, and we applying that we have CPM as the same, so 1 over g squared is the same 1 over g squared for each CPM. So in principle, you can discuss even more. So because of that, you have kind of the symmetry. I mean, because you can transform between different CPM. Okay. Here it is the same Lagrangian, but it was called gauge formulation for two-dimensional model. You have this n field. Here you have sigma field. I don't know if you remember this large n solution for two-dimensional model. It is this form is convenient for this large n solution. That's why it's in this form. So remember that in normal CPM you have either you can say that it is like n squared equal 1, or instead you can consider a model where you have kind of fundamental field, complex field instead of n and like a W. For SU2, for example, and it would be the same model, and it would be what I call gauge formulation. So here, it appears, you see, because like a vector field, a new here. Okay, but you can check that it is the same two-dimensional model. Now. I mean, you can discuss, I mean, the same number of components accounted for these constraints. I mean, you see here the constraints is the square, 1 over g square. Fermions are transversal to this one. Okay, and it count entered to the counter. Now,
sorry, could you remind me where's what's counting from?
Sorry?
So I mean, the third term, the first term in the third line, that's a Payel-Yakos term.
Yeah, I think it is, yeah. Yeah, it should be the Payel-Yakos term. I think it's, you're right.
I'm just wondering, I'm just trying to understand where that's coming from.
No, but we will see it. When we will come to the solution, it will be easier to look here. Okay, so you see, I'm trying to write this Lachian solution. So if you integrate over the same field, which are n quadratically, so you can integrate over them, and you have this ratio of determinant, and this one loop potential is written here. Okay, so I mean, okay, and then Lachian solution corresponding that like where derivative potential equals 0, it fixes you what is df, and here the expression for effective potential, if you have 0 deformations, then you have this df equals 0, and you have this vacuum average of sigma by face. You see, the n possible vector. Okay, for each CPN minus one, you have n possible vector. Let's start with one CPN without kind of connected model. Then you can check that from here you will find out that I'll say that you indeed have a spontaneous breaking of supersymmetry, and you are not staying this zero energy. You have masses Gaussian, and it is a normal situation for this type of 0-2 model. If we consider n larger than one particular two, then you can find out, you see, because df non-zero, it automatically means that supersymmetry is broken. Here, we are looking for the one where df equals 0, and sigma equal this one, so then sum of this one, which is the vacuum energy, also stays 0. Okay, and but I'm sorry. Yeah. For n equal 2, in particular, we have n square of this free vacuum. Out of this n square possible vacuum, when you distribute them between different groups, the n supersymmetric one. And n minus 1 is positive energy and supersymmetric vacuum. Okay, so you have possibility. I mean, okay, you have both, but at least you have one with supersymmetric, and it is the one with the lowest energy. Okay. So here it is an expression for the spectrum of this model. So here, as a result of the solution, you can find out that masses are equal. This lambda, it's like QCD lambda. I mean, the one which related to cutoff. I wrote expression before. So you have masses of scalar field and fermionic field equal lambda, and in this what I am discussing here, it is a 2-2 series where there is no deformation. Now you have this. I mean. You see, you have additional stuff which becomes propagated field with masses 2 lambda instead of 1 lambda. Okay. Now when we go to deform CPM, then we have you see that mass of C becomes different from mass of M. And in particular, at large U, you see the behavior is such that this lambda must be square root of U, and here it is exponential dependence. Okay, and you can say that Gaussian is presumably this lambda field in this case. It was for say n equal 1, where it was no, I mean, where it was this spontaneous supersymmetry rate. When we have n equal 2, you can see here, I mean, the multiplication of the formula, and you can find out that there is masses like Morin-Fermi combination of lambda and theta, but it's not Gaussian. So there is no this how say residue for supercurrent to Gaussian. So there is no supersymmetry breaking, and we were trying to understand, in other words, why generically there is this supersymmetry breaking, but not in this special case that we can find out supersymmetry preserved. If we will calculate this what's called Witten index, number of vacuum, fermionic and bosonic vacuum, we can find out that Witten index equals 0 in this series. Witten equals 0 implies that supersymmetry could be broken. It does not have to be broken, but how say, if it would be non-zero, then it could not be broken. But here it equals 0. But we see that while it could be broken, it's not broken for this particular case. So to understand this, we introduced what's called elliptic genus. And it is the one. It is like, you can say that it is a more general type of Witten index which involve this conjugation. Zeta goes to where fermionic field are changing sign and bosonic field are not changing sign. So then let's introduce an index which is -1 to the power, but also contains p. Okay, and we can check that that this index doesn't vanish in the case where supersymmetry is preserved, and that is a possible explanation. While with this additional index, while supersymmetry is preserved, because you can say that this extended index is not zero. Okay, now I'm coming to my conclusion. I try to demonstrate this exact relation with the function. Between, let us say, for relation between beta function and anomaly dimension in case of n equal 0, 2 models, and it was an analog of an SVC beta function, but I did try to mention this a little bit of kind of special trick which appears there in this heterotic model. Okay. In particular, I mentioned that you have, say, to calculate two-loop anomaly dimension, you have a three-loop beta function, not because of this exact relation. Okay. And the last part which I shortly discussed was this squirrel-like connected sigma model where supersymmetry is spontaneously broken. Okay. I mean, if it would be no quiver, but I mean, the normal CPN would be broken, but this querization helps you to protect supersymmetry. And okay, explanation was this, in particular, this special type of index associated with, I mean, extended Witten index in particular. Okay, so I'm not sure whether you find it's interesting, but okay, for us it was kind of a real effort to go through this. It was also some stuff associated with, kind of differential anomaly, which I didn't discuss here, but it was a lot of efforts we spent there. In particular, this my former student Jin Chen, he put a lot of efforts in studying this, but I needed this one. Okay, thank you.
Any questions? I have a question. I got a little bit confused right when you're talking about the quarter-like models. So I mean,
Yeah.
The Goldstina there is the Goldstina associated with functions breaking 0, 2.
Yeah, right.
Right. So
Yeah.
can you remind me, like, how do you identify it?
No, I mean, okay. Once you have, say, Supercard, right? The tone linear in the field there, it is would be a Goldstina, right? Okay, you can.
Okay, you just choose it. Okay.
Yeah.
Right.
Yeah. So no, and generically because you have few mass experiments, it could be a combination, but you can follow up which particular combination enters, which one plays a role in Goldstina. So because I mean, you see that even when supersymmetry spontaneous breaking not occur, we still have mass experiments. Yeah, but they are not associated. I mean, I think that, for example, if you will make something like similarity between different CPN, it would be already sufficient not to preserve it. You see, because then you could be back to the case similar to one CPN. Here we played with CPN which was all the same.
Okay.
And then it helped to preserve this.
Any other questions? All right, let's thank our speaker again.
Thank you.
Something I should